Welcome to our deep dive into problem-solving agents in artificial intelligence. In this chapter, we'll explore how intelligent agents tackle complex tasks by searching for solutions. We'll break down the core concepts from what it means to search, to how agents decide on actions that lead them closer to their goals. By the end, you'll have a clear understanding of how AI agents formulate problems, evaluate possible actions, and select the best path forward. Let's begin by setting the stage for what problem-solving in AI truly involves. The heart of problem-solving in AI lies the concept of search. Search refers to the process of exploring possible sequences of actions to reach a desired outcome. When an agent faces a challenge, it doesn't just act randomly, it systematically considers different possibilities, weighing each one to find the most promising path. This process is essential for tasks ranging from navigating a map to playing chess. By understanding search, we unlock the foundation of intelligent decision-making in machines. Before an agent can solve a problem, it must first define what the problem actually is. This step, known as problem formulation, involves deciding which actions and states to consider based on the agent's goal. By clearly outlining the problem, the agent sets boundaries for its search, making the process more efficient and focused. This careful planning is what separates intelligent agents from simple reactive systems. Every problem-solving agent operates within a world made up of states. A state represents a specific situation or configuration at a given moment. The collection of all possible states forms what we call the state space. By navigating through the space, the agent explores different scenarios, searching for a path that leads to its goal. Visualizing the state space as a network helps us grasp how agents move from one state to another. AI agents use a variety of search strategies to find solutions. These strategies can be broadly categorized into informed and uninformed approaches. Informed strategies use additional knowledge to guide the search, while uninformed strategies rely solely on the structure of the problem. Local and adversarial search strategies also play important roles, especially in complex or competitive environments. Each approach has its strengths and is suited to different types of problem. Let's break down the difference between informed and uninformed search strategies. Uninformed search, sometimes called blind search, explores the state space without any extra information about the goal's location. In contrast, informed search uses heuristics, educated guesses, to prioritize which paths to explore first. This can make the search much more efficient, especially in large or complex state spaces. Local search strategies focus on improving a single solution by making small changes, rather than exploring the entire state space. These methods are especially useful when the state space is too large to search exhaustively. By iteratively tweaking the current solution, local search can quickly find good, if not always optimal, answers to complex problems. Competitive environments such as games, adversarial search strategies come into play. Here, agents must anticipate the actions of opponents and plan accordingly. These strategies involve looking ahead at possible moves and countermoves, aiming to maximize the agent's chances of success while minimizing the opponent's. Adversarial search is a cornerstone of AI in game playing and strategic decision-making. Not all search strategies are created equal. Evaluating their effectiveness involves considering factors like completeness, optimality, time complexity, and space complexity. By analyzing these criteria, we can choose the best strategy for a given problem, balancing speed, accuracy, and resource use. This evaluation process is crucial for building efficient and intelligent agents. One common challenge in search is the risk of revisiting the same states over and over. This can waste time and resources, especially in large state spaces. Intelligent agents use techniques to avoid repeated states, such as keeping track of visited states or using constraint satisfaction methods. These approaches help streamline the search and prevent unnecessary loops. Constraint satisfaction search is a powerful technique for solving problems with specific requirements. Instead of searching blindly, the agent applies constraints to narrow down the possible solutions. This method is widely used in scheduling, planning, and resource allocation tasks, where certain conditions must always be met. Problem-solving agent is a type of goal-based agent. This means it decides what to do by finding sequences of actions that lead to desirable states. Unlike simple agents that react to immediate stimuli, goal-based agents plan ahead, considering the long-term outcomes of their actions. This forward-thinking approach is key to intelligent behavior. Problem-solving agents use atomic representations, treating each state of the world as a whole with no visible internal structure. This simplifies the problem, allowing the agent to focus on transitions between states rather than the details within each state. Atomic representations are especially useful in environments where the complexity of internal details would otherwise overwhelm the search process. At the core of problem-solving agents are two fundamental concepts: problems and solutions. A problem defines the challenge the agent faces, while a solution is the sequence of actions that leads to the goal. By clearly distinguishing between these two, agents can systematically approach even the most complex tasks. Intelligent agents are designed to maximize their performance measures. This means they adopt goals and strive to satisfy them as effectively as possible. By constantly evaluating their actions against a performance metric, agents can adapt and improve over time, ensuring they remain effective in changing environments. Goal formulation is the process by which an intelligent agent decides what goal to pursue. This decision is based on the agent's current situation and its performance measure. By carefully selecting goals, agents ensure their efforts are directed toward meaningful and achievable outcomes. Once a goal is set, the agent must formulate the problem, deciding which actions and states to consider. This step is crucial for focusing the search and avoiding unnecessary complexity. By defining the problem space, the agent lays the groundwork for efficient problem solving. The search process involves looking for a sequence of actions that leads from the initial state to the goal. This is where the agent explores different possibilities, evaluating each one based on its potential to achieve the desired outcome. The search process is the engine that drives intelligent decision-making. A search algorithm is a method that takes a problem as input and returns a solution in the form of an action sequence. Different algorithms are suited to different types of problems, and choosing the right one can make a huge difference in efficiency and effectiveness. Let's bring these concepts to life with a classic example, the Romania Turing problem. Imagine an agent with a non-refundable ticket to fly out of Bucharest the next day, currently located in Arid. The agent's goal is to reach Bucharest before the flight. To do this, it must plan a route through various cities, deciding which roads to take and in what order. In the Romania Turing example, the agent first formulates its goal, be in Bucharest before the flight. Next, it defines the problem by identifying the states, the various cities, and the actions driving between cities. The agent must then search for a sequence of cities that leads to the goal. Here's a visual representation of the Romania Turing problem. The road map shows the cities and the connections between them, forming the state space the agent must navigate. Each city is a state and each road is a possible action. The agent's challenge is to find the best path from Arid to Bucharest. A well-defined problem in AI is one that can be described using 5 key components. These components provide a clear framework for the agent to operate within, ensuring the problem is structured and solvable. Let's explore each of these components in detail. The first component of a well-defined problem is the initial state. This is where the agent starts its journey. In the Romania example, the initial state is being in Arid. Clearly defining the starting point is essential for planning the path to the goal. The second component is a description of the possible actions available to the agent. For each state, the agent must know what actions it can take. In our example from Arid, the agent can choose to go to Sibiu, Timisoara, or Zărăunt. These choices define the agent's options at each step. The third component is the transition model, which describes what happens when the agent takes an action. This is specified by a function that returns the resulting state after an action is performed. For example, if the agent is in Arid and chooses to go to Zărăunt, the resulting state is being in Zărăunt. A successor state is any state that can be reached from the current state by taking a single action. In the Romania example, moving from Arid to Zărăunt creates a new successor state. Understanding successors is key for building the state space and planning the agent's path. The initial state, actions, and transition model together define the state space, the set of all states reachable from the initial state by any sequence of actions. This state space forms a network or graph with states as nodes and actions as links. Navigating this space is the essence of problem solving in AI. A path in the state space is a sequence of states connected by actions. The agent's goal is to find a path from the initial state to the goal state. Each step along the path represents a decision, and the entire sequence forms the solution to the problem. The fourth component is the goal test, a function that determines whether a given state is a goal state. In the Romania example, the goal test checks if the agent is in Bucharest. This test guides the agent, letting it know when it has succeeded. The fifth component is the path cost function, which assigns a numeric cost to each path. This cost reflects the agent's performance measure. For the Romania agent, the cost might be the total distance traveled. The agent aims to find the path with the lowest cost, known as the optimal solution. Step cost refers to the cost of taking a specific action from one state to another. In the Romania example, the step cost might be the distance between two cities. By summing up the step costs along a path, the agent can evaluate the total cost of reaching the goal. A solution in AI is a path from the initial state to a goal state. This path is made up of a sequence of actions that transform the initial state into the desired goal. The quality of a solution is measured by its path cost, with the optimal solution having the lowest cost. An optimal solution is the best possible path from the initial state to the goal, as measured by the path cost function. Finding the optimal solution is the ultimate aim of many problem-solving agents, ensuring the most efficient and effective outcome. To recap, a well-defined problem in AI consists of the initial state, possible actions, transition model, goal test, and path cost function. Together, these components provide a structured framework for intelligent agents to operate within, making complex problem-solving possible. The journey from problem to solution involves careful planning, systematic search, and constant evaluation. By following the structured approach outlined in this chapter, agents can tackle even the most challenging tasks with confidence and efficiency. Problem-solving agents are used in a wide range of real-world applications, from route planning and logistics to game playing and automated decision-making. Their ability to search for optimal solutions makes them invaluable in both everyday and specialized tasks. Despite their power, problem-solving agents face challenges such as large state spaces, incomplete information, and time constraints. Overcoming these obstacles requires smart strategies, efficient algorithms, and sometimes creative thinking. To improve search efficiency, agents use techniques like pruning, heuristics, and constraint satisfaction. These methods help reduce the number of states explored, saving time and resources while still finding high-quality solutions. Some problem-solving agents can learn from experience, adapting their strategies based on past successes and failures. This learning capability allows agents to become more effective over time, handling new and unexpected challenges with greater skill. Heuristics play a crucial role in informed search strategies. By providing educated guesses about which paths are most promising, heuristics guide the agent toward the goal more quickly. Designing effective heuristics is an art that combines domain knowledge with algorithmic insight. In practice, constraint satisfaction is used in tasks like scheduling, resource allocation, and puzzle solving. By enforcing rules and limitations, agents can quickly eliminate impossible options and focus on viable solutions. To sum up, problem-solving agents in AI rely on structured problem formulation, systematic search, and careful evaluation to achieve their goals. By mastering these concepts, we can build intelligent systems capable of tackling a wide range of challenges. In the next chapters, we'll explore advanced search techniques, optimization methods, and real-world case studies. These topics will further enhance your understanding of how AI agents solve problems and make intelligent decisions. Thank you for joining us on this journey through problem-solving agents in AI. By understanding the principles of search, problem formulation, and solution evaluation, you're now equipped with the foundational knowledge to explore more advanced topics in artificial intelligence. Stay curious and keep learning.